Welcome to the review lecture or review session for ECE 442-542. If you're taking this through Examity, this is a pencil to paper exam. You will see the exam on the screen, or you'll download the exam. Anyway, you'll have access to the exam and you'll write your solutions on blank paper. Make sure you have a way of scanning that after you're finished with the exam and uploading that or dropping that, submitting that scanned material into the Dropbox on D2L. Obviously, if you're taking it in class, you'll just hand in your exam. You will bring, and we've already talked about this, so I'm just going to show it to you there and you can read it, and you're not allowed the obvious material. The topics, I would recommend that you look at the list of topics for exam number 1 on the D2L class website, and it sort of walks you through what you will be held accountable for on the exam, but the practice exams also give you a strong indication as to the content or the topics or the material that you will see on exam number 1. And if there's a long list of practice exams, if you get a few years into the past, some of those exams may not be covering exactly the same topics that we did. So pay attention to the specific problems that are called out in the title or the subheading of each of those exams. Don't get really nervous about, well, I don't even remember seeing this. Well, it may be that we haven't talked about that yet in this semester. So just pay attention to the ones that are called out. A way to study would be to take some of the previous practice exams from scratch and seeing how well you do. Then you might start reviewing homeworks 1 and 2, and then after that go back through the lecture materials. And today's lecture that we had just before this, the main thing to focus on is really that sampling period. I mean, you should be able to take a difference equation and find its z-transform to find a transfer function. A lot of those steps you should be able to perform, but the main thing is working through some of that, and given a particular set of poles, what sampling rate do you want? And we'll talk about that now, I think, in this review session. So let's get started by going through some concepts or ideas relative to the review. And I really appreciate people actually filling out the quiz for the review session. I may hold it up for those in class, but there were about 23 students that submitted some questions that wanted reviewed, and many of those, if I had to put a weighting on any of those, it would be state space, state space, state space. What's the state space representation and how do we use it and what is it good for? And really, you need to be able to sort of work your way through this 4-corner diagram of representing a system. You should be able to start with difference equations and create a block diagram, and we'll try to go through an example that illustrates that. If you have a block diagram, an all-delay block diagram, you should be able to produce a state space representation. And these notes and this video will be uploaded, so you don't have to frantically try to copy everything down. I'm really wanting you to get the idea behind these. Maybe when we start doing some examples, you'll want to start writing things down. But to get a state space representation, state space representations are not unique. But one way to find one would be to label the outputs of your delay blocks as individual state variables. And then you can find these state space representation. If you wanted the transfer function, you could go multiple ways. You could actually z-transform the difference equations, or you could start with the state space representation and z-transform that and end up with this expression for g of z in terms of these system matrices, phi, gamma, h, and j, in this expression for g of z. But you should be able to start with one of those locations in this four-corner diagram and get back or around to different locations in the diagram. If I gave you a transfer function, can you now find the difference equations? If I gave you a transfer function, you should be able to find the difference equations and then find a block diagram and then find a state space representation. You should be able to work your way around that particular four-corner way of modeling a given system. If I give you a difference equation, you should be able to come up with different ways of solving that. I might say, what's the or find the solution to a homogeneous equation. Or maybe I force this equation with a non-homogeneous. So we now have a forced equation with initial conditions. What's the structure of the output if it's an unforced difference equation? What does that look like? Or what's that based on? If I said, what's the structure of y of n for an unforced difference equation, what would you be looking for in terms of helping you find that structure? Pardon? Oh. At what time does the building lock? Were all doors locked, or was the... Wow, I'm glad I got back in. I wondered about that. So it must lock at 7, probably because there's nothing in this classroom scheduled. Huh. Shh, shh. No one knows that we're in here. All right, so back to the unforced structure of our system. What if I now z-transform that difference equation, and what would I use that z-transformed expression to find the structure for y of n, or how could I use that? Can you find the roots of your characteristic equation and find the natural modes? That now gives you the structure of your output response in an unforced situation. If you're in a forced situation, you combine those natural modes with what? And the structure introduced by your forcing function or your excitation. So now you have the natural modes and the forced modes. Here's the part that we want to be clear on. Selection of the sample period. People have the rule of thumb down. That's 30 times the closed loop bandwidth. But what if I now gave you, and all of these labels, the different ways of putting units on the sampling frequency omega sub s, that's in radians per second. 2 pi is this scaling factor, that's in radians per sample or radians per cycle, that scales the sampling frequency in hertz. And our sample period, capital T, is in seconds per sample. Suppose now I give you this collection of poles. Here's the S-plane. And I say, I want you to sample this system or find the capital T associated with this system. How would you go about finding capital T, the sample period, if I gave you this plot and I labeled it so that you could find these particular locations for S1, which is a real pole, S2 as complex conjugate, and S sub 3 as a complex conjugate pair? Can you now talk about these particular poles relative to how they impact the system's behavior or response. If I ask you to identify the dominant, let me see if I can now start collecting these. So here's one set. Here's another set. And here's a third pole. Relative to those particular pairs, can you tell me which of those, the yellow, the blue, or the magenta, dominates the time domain behavior? Which one dominates the behavior of your system? And what does dominant mean? Does the dominant go with the fastest or the slowest? The slowest. So the dominant pole is the slowest, and which one of these is the slowest pole? The one closest to the origin. This is in the S-plane, so this particular pole is actually the dominant pole, or the slowest. Does that help us for sampling purposes? Which of these collections, yellow, blue, or magenta, do you need to focus on if we're sampling? Pardon? Yellow. Why yellow? It's the fastest. So the yellow is the fastest, and that's the one that we really want to focus on if we were now trying to sample. So let's now say, what is omega sub c? And we'll assume that S1, S2, and S3 are closed loop poles. And I'm going to go ahead and also assume the following relationship. Each of those poles, S1, S sub 2, and S sub 3, have a hypotenuse, or a distance away from the origin, a radial distance. I'm going to assume that the magnitude of S1 is less than the magnitude of S2 is less than the magnitude of S sub 3 as I've drawn them. So here's, let's say, R1, R2, and R3. Which of those would I use for omega sub c? S3 or R3, right? The magnitude. So now I'm looking at the magnitude of S3, which is really, if we had its real part and its imaginary component, we could just find the hypotenuse from that. And then if we wanted to sample, we would use that relationship. Omega sub s is 2 pi over cap t, and we know what omega sub c is. Now we can find capital T. That's the only unknown in that equation. And that would be if I just gave you a transfer function h of s, or if I gave you its pole zero pattern, you could now find which poles are the furthest away in the S-plane in order to determine what capital T is, the sample period. What about stability? And here we're interested in bounded input, bounded output stability. Suppose now we have a transfer function or a system h of s and has all of its poles. Oh, so for bounded input, bounded output stability, here's really the definition. The system, H of S, has all of its poles where relative to the unit circle. Here the key word is inside, and this is now our, in the z-plane, so that if we had something that was that blue dashed is supposed to be the unit circle. Are any of these plots stable, unstable, or can you say? The one on the left, is that stable or unstable? This one's stable. All of the poles are inside the unit circle. What about the right one? That one's unstable. What if you actually had a different, what if you had a pole right there on the unit circle? Is that bounded input, bounded output stable? No, because you could actually find a bounded input, a constant, that would then introduce another really pole right there on top of it, and now you have an unbounded response. So for bounded input, bounded output stability, we need all of our poles to be inside the unit circle, not on the unit circle. Now I should say that you may actually, for determining sampling period, capital T, you might need to analyze the equations of motion or find a transfer function for a given system, and in particular it might be a given circuit. So you should be able to find just a generic transfer function. You don't have to look at a specific transfer function. You just need to find a transfer function for a given circuit. But in general, I would like you to be comfortable with a mechanical, electromechanical. This was our DC motor from homework number 1. But on this exam, you're probably going to be more focused on finding a transfer function from a circuit and just looking at the denominator and saying, okay, what are the poles of that denominator? I'm sorry, what are the roots of that denominator polynomial? What are the poles of my system, and which ones are the fastest? And use that to determine your sample period, capital T. You'll need to be able to do a Z-transform for many different purposes. One might be given a generic waveform or a general waveform or a function of n in the form of some x of n, can you find the Z-transform? You should also be able to find the Z-transform of a difference equation, which we've done earlier. Given a y of n plus an alpha 1 y of n minus 1 equaling a beta 0 u of n plus a beta 1 u of n minus 1. Or you should be able to then find the z transform associated with a block diagram if that block diagram was an all-integrator block diagram. And that really just means that you have to convert these all-delay blocks or replace them with this z to the minus 1 operator, where this is now the time domain and the z to the minus 1 puts you in the frequency domain. Taking the z transform of a difference equation allows you one way to actually find a transfer function. You could also find it from block diagram algebra. Or performing the z transform of the difference equation, as we just mentioned. Or, in fact, if somebody had given you, or if you found a state space representation, can you now plug in the appropriate matrices into this expression G of Z, which is now the output matrix Zi minus the system matrix phi inverted times the input matrix plus the direct feed-through matrix J. I might also give you a problem where you have to do a settling time determination based on discrete time setting. For example, suppose I now provide you with a transfer function or this z-plane pole 0 plot, and I now have a couple of pole pairs in this diagram. And maybe this is 1 and this is minus 1. If I'm talking about settling time, what do I definitely need to have true relative to those pole locations? They have to be inside the unit circle. So let's say that these are, maybe I should have made these a little bit different angles. Those two in the suppose that this is R1 and this is now R sub 2. Again, I can circle that complex conjugate pole pair and I can circle that. Which of these pole pairs will dominate the system response? Yellow or blue? Or which one corresponds to the slowest set of pairs? R1 or R2? So if we were trying to do the settling time for this, what's our settling time formula? Y of capital N is equal to something times y of 0. What's the something that relates the initial value to the final value that's now within 1% of where we wanted to be? If that's our formula, which R do we plug in? R sub 1 or R sub 2? Or which one's the slowest pole pair and which one's the fastest? Can we identify that? R1 is which? Slowest. So this is now our slowest. If that's the case, I only have 2 pairs, so this must be the fastest. And why is that? Why is this pair faster than the R1 pair? Just plug in some typical numbers. Let's say R sub 2 is 1/4 for a radius and R1 is 3/4. As you raise those 2 fractions to higher and higher powers, the 3/4 collapses much slower than the 1/4. That's how to sort of intuitively convince yourself of which one's the slowest and which one's the fastest. The slowest one is actually going to be the dominant pole pair. Now that I've said that, which R do we pick to determine the settling time? R sub 1 or R sub 2? We pick the slowest one, don't we? The fastest will decay long before the slowest in relative terms. So to get the settling time, we would focus on the one furthest away from, or the one closest to, the unit circle. Yes? So the slowest is actually the one furthest away from the origin, but still inside the unit circle. So you need, in order to be speaking of a settling time, you have to have a stable system. So your poles all have to be inside the unit circle. And your one that's going, we're going to say the one that dominates has the largest radius and still inside the unit circle. In this case, R1 is, I'm saying I've drawn it hopefully, inside the unit circle, and that's going to be the one that dominates the response. Questions on that? Yes.
But if we just had, I guess, yeah, R2 or R1 was outside of the unit circle, we were just saying.
If our poles associated with R1 was outside the unit circle, we couldn't even talk about a settling time. It would be going unbounded. And so if I now give you a transfer function without giving you poles, you could now find the poles of that transfer function and put them into this kind of a thought process. You would say, oh, where are my poles located and which ones have the largest radius? If they're all stable, then you look at the largest radius, use that in R1, and then use that to find your settling time, your 1% settling time. What is capital N? You can solve for that. Use taking the log of both sides, etc. Questions on that? Now I'm not sure where I want to go, but well, I know where I want to go, and I know I'm not going to ask you where you want me to go, but I was going to start with now finding a state space representation, unless there's another question. So now would I ask you to derive a Z transform of a signal? Yes, that's the waveform x of n. But most of these will be for waveforms that are defined for non-negative values of n. After exam number 1, we'll worry about indices that are negative, indices that are positive, and indices that are on both sides of n equal negative and n positive. And then we'll have different regions of convergence. But here, the regions of convergence, if this, let's say, is x of n is defined for n greater than or equal to 0, then your region of convergence is going to be outside some radius influenced by the largest diameter pole associated with capital X of Z. Suppose now that we wanted to find a state space representation for a given difference equation. And in fact, why don't I go back to a previous exam which will stretch our application of this a little bit further. What if I have now a coupled set of difference equations? And this is problem number 4. I guess it's 4A from the spring 18 exam number 1. So that now I have, let's say, W1 of n plus 1 equaling 0.5 W1 of n plus W2 of n minus 1 plus 2 U of n minus 1 and W sub 2 of n plus 1 is equal to W1 of n plus, whoops, it's minus 4 W2 of n plus 3 U of n. And maybe Y of n is some linear combination of the W's. 5 W1 of n minus W2 of n. So this is not just a difference equation relating an input to a variable y. This is now an interrelated collection of coupled difference equations. And now it's like, okay, now what do I do? How do I approach this? One way that I might suggest is to say, let's do this by what I will call nesting delay blocks. And I'm going to try to talk our way through that nesting process, but the process will assume that everything that goes into a delay block eventually needs to be restricted to just an undelayed version of the input, U, an undelayed version of one of the state variables, W1, and an undelayed version of the other state variable, W sub 2. So we're assuming that those waveforms are available. And what we may want to do is simply rewrite these forms to maybe have the highest power of the argument for W1 and W2 be actually little n and not n plus 1, so that everything now looks delayed. And we can do that if we're consistent with how we change the index in our argument. Meaning, let's rewrite the first equation as W1 of n. We've now reduced the argument on the left-hand side by 1. We've changed n plus 1 to n. That means when we see this 0.5 W1, what does its argument become? It's now n minus 1. We have plus W sub 2 of n minus 2. And we have plus 2 U of n minus 2. Is it clear where that came from? We can always adjust the arguments of our difference equation as long as we do the equivalent adjustment inside the argument of each term. Then we can adjust W sub 2 to be whatever it needs to be. W1 of n minus 1 minus 4 W2 of n minus 1 plus 3 U of n minus 1. Are we okay with that? Now what we want to do is try to nest delay operators so that the argument or that delay operator is only operating on the signals that we have available, U, W1, and W2. Meaning, U of n minus 1 will be the same as D of U of n. Is that clear? And if I now had D of U of n, what does that equal? U of n minus 2. So that's the idea of nesting delay operators. What I want to do is write that first equation, W1 of n, as a collection of weighted or delayed versions of W1, W2, and U. So let me start with this. Well, I can start in many different ways. Let me say there's a delay on the very first one, and that would be 0.5 W1 of n. Is it clear where that came from? Now that D that's on the left of that curly bracket is going to also operate on the delay associated with W2 of n minus 2 and 2 times U of n minus 2, so that I now have plus another delay running out of brackets. So let me create a new one. This is now going to be W2 of n plus 2U of n. And now I'm done with nesting nesting delays of that first difference equation. Is that clear what I've done? Let me do the same strategy or approach to the next difference equation, and how many delays do I need to introduce there? Looks like just one to get me what I need on the inside or the inputs to that delay operator. So now W sub 2 of n is now going to be a delay of W1 of n minus 4W2 of n plus 3U of n. And suppose now that I actually have available to me W2, W1, and U all at time n. So let me first look at implementing that. And eventually I want to have coming out of all of these, or we could do it many different ways. I could say, well, let me try it a different way so that you can read the solutions later and say, oh, that's not how you did it. So let me do it maybe a different way and say, what if I now say that W1 is right there, and that's coming out of a delay block from the first equation. Going into that delay block, the input to that delay block is 0.5 times W1, and I can generate that this way. And now I need another input to that summing junction to be the output of another delay block, where that delay block has as its input 2 times U of t. Suppose I now have U of t up here, and I say, oh, I need to multiply that by 2. And I also need a W of W2 of n. So let me say that this is now W2 of n. Is it clear where that came from? That's now the top coupled difference equation in a delay, all delay form, just using U, W2, and W1. But now W2 needs to satisfy this right-hand side. And that can now be the output of a delay block. Where the input to that delay block is 4 minus 4 weighting that. So now here's this summing junction, and I'm going to say, well, that's a weight of minus 4. W2, it's going to be W1. I can pull that down here. And it's 3 U of n. So let me take this U of n. This is really clean, isn't it? 3 there. Is that okay? Oh, and I still need to do y, don't I? Oh boy. So y, if I need it, where was y? Is 5W1 minus W2. So to generate y, I've already forgotten what it was. Y of n was 5W1 minus W sub 2. So now I come up here. Maybe what I want to do is scale that by minus 1 so I don't have to have signs on my inputs to summing junctions. That is now my all delay block diagram associated with that coupled set of difference equations by using nested derivatives, nested delay blocks. It's getting late. Are there questions on that? It's very University of Arizona focused. It's red and blue. But that's how you can now connect the input to the output y from a set of coupled difference equations. If you wanted now a state space representation, you simply label the outputs of your delay blocks as state variable components. So that now this one I could say is x1 of n. Here is x sub 2 of n. And here is x sub 3 of n. Which means that right here is what? x1 of n plus 1. Here is x sub 2 of n plus 1. And here is x sub 3 of n plus 1. And I can now say that x1 of n plus 1, x sub 2 of n plus 1, and x sub 3 of n plus 1 are some linear combination of x1, x2, and x3 at n plus u of n. What's x sub 1 of n plus 1? Is it 0.5 times x1 of n plus x sub 2 of n and 0 and 0? What about x sub 2 of n plus 1? Is that okay? And then finally x sub 3 of n plus 1 is minus 4 x sub 3, 3u of n plus x sub 1 of n. And what is y of n? The way I've labeled my state, or delay blocks, y of n is going to be five x1, no x2, and minus 1 x sub 3. Is that okay? And that's now a way to create a state space representation from a coupled set of difference equations. And if you wanted to, you could now do block diagram algebra. You could do the formula. Here we had 0 times u of n. This is now our j. This is our h. This is our phi. And this is our gamma. We could use that now to find g of z is equal to h zi minus phi inverse gamma plus j. Are there questions on that? Do you want to see it done again with a different example, a simpler example, so that you can now kind of follow it along? Suppose that I now said, here's another equation. Say y of n is equal to 1.4 y of n minus 1 minus 0.45 y of n minus 2 plus u of n minus 1 plus 1/2 u of n minus 2. This one is actually maybe more straightforward because it's not coupled. But if we do the same strategy and try to nest our delay blocks, how many delay blocks do you expect we should be getting or using? Probably 2. So now let's say y of n is now going to be a delay block of 1.4 y of n plus u of n. Is it clear where that came from? And now I've accounted for this and that. So you could start even getting rid of those mentally if you wanted to by underlining or highlighting. Now I have one more set or delay, so this one's now nested inside the curly bracket, and I have minus 0.45 y of n plus 1/2 u of n. Are we okay with what I've done? What if I now wanted to create, well, how did I do this before? I said, well, let me start with y of n over here and assume that I have u of n coming in from here. Y of n is now the output of a delay block, and what's the input to that delay block? 1.4 y of n u of n, and then it's also the output of another delay block. And the input to this delay block is what's right there. And that is going to then be one-half times u of n and minus 0.45 y of n. Is it clear where that came from or how we built that? Now, if we want a state space representation, what do we do? Label the outputs of our delay blocks. So I could label this as x1 of n, and this is x sub 2 of n. And state space is not unique. Somebody else could have just interchanged those, and that would have been equally valid. They could have said y of n is actually x2 of n, and the leftmost delay block's output I'm going to say is x1 of n. That's fine. That's an equally equivalent state space representation. But now if I said what's the state space representation, I now have x1 of n plus 1, x2 of n plus 1 equaling some linear combination of x1 and x2 and a linear combination of u. What makes up x1 of n plus 1? That's the output signal of the rightmost summing junction. That's x1 of n plus 1, and I just have to add up all the input signals. One of those input signals is u. Another one is x sub n, and the other one is 1.4. X sub 2 is now 1/2 and minus 0.45. What's y? Zero there and 1 there. And now this is phi, this is gamma, this is h, and that's j. Is that system stable? Is that a valid question? Could you answer that given this information? Or now I might say, oh, here's a difference equation. Is that BIBO stable? You could z-transform this and find the characteristic equation, find its roots, and if they all have magnitudes less than 1, it is. If you now have this form, you could say, oh, the eigenvalues of phi will tell me whether or not my system is stable or not. And now I just have to go back to 310. Did you do eigenvalues in ECE 310 or any math class? Pick your favorite math class. Now I'm looking at lambda I minus phi, the roots of that, so that I now have lambda minus 1.4 minus 1, 0.45, and this is lambda. Lambda times lambda minus 1.4 minus a minus 0.45. Or I now have lambda squared minus 1.4 lambda plus 0.45. And that factors. So now I have roots of my system matrix. One is at lambda 0.9 and the other one is at 0.5. Both of those have magnitudes less than 1, so the system is stable. And now I might say which of the roots dominates, or which root is dominant. 0.5 or 0.9? It's the biggest one. They're both inside the unit circle. That one dominates. What's the settling time? That's this relationship where now this is r to the n times y of 0. So now we have r to the n is equal to 0.01, and r was the 0.9. That was the dominating root, and we want to know what n makes that left-hand side less than or equal to 0.01. Or we can use some logarithms to solve that. And n now becomes minus 2 log base 10 of 0.9, and that ends up being 43. So in 43 sample periods, we would be settled. We would have our 1% settling time. And again, you could find the the z-transform of the difference equation, find the transfer function, find the roots of the characteristic or the denominator. They will also be 0.9 and 0.5, etc. What if u of n was equal to 0.7 n cosine pi over 8n for n greater than or equal to 0? What is the structure of y of n for that particular difference equation that we had? What was our difference equation? Let me write it down again. We had y of n was equal to 1.4 y of n minus 1 minus 0.45 y of n minus 2 plus u of n minus 1 plus 1/2 u of n minus 2. And if you z-transformed all of that, you would get something like that, so that g of z is equal to y of z over u of z and if you wanted to rewrite that in terms of positive powers of z, and finally you might have then in factored form something like that. If that's now our transfer function, g of z, what's the homogeneous structure or the natural behavior of the system? What's the structure of the homogeneous solution? And the structure, I'm not asking you to find the exact homogeneous solution, but what do you need to use to find the structure of your homogeneous solution? It's actually on the screen, isn't it? It's the 0.9 and the 0.5. We could say, oh, the structure is now alpha 1, 0.5 to the n plus alpha 2, 0.9 to the n for n greater than or equal to 0. That's the homogeneous solution structure. What's the particular structure? What's the structure that's going to appear because of the way that we forced that system or excited that system? We said we were exciting it with this input. So the response due to that input y sub p of n is now really just a sine and cosine weighted of that same exponentially damped cosine that we excited the system with. We could then say that the particular would be a beta 1 0.7 to the n cosine of pi over 8n plus a beta 2 0.7 n sine. That's now the structure that we would expect for the system in its excited form. Yes?
Can you go over how you got that, and is that different depending on what U of n is?
So the particular structure depends, well, I shouldn't say naturally, but it is really associated with how you are exciting the system. So it definitely is going to have exactly the same structure as your excitation, U. It's just when you shake something, there's going to be some sines and cosines present, or there would be a delay in the argument of the cosine if you had a cosine piece. The only caveat to that is if your natural system had similar modes as your excitation, then you would have to put some independence into your particular solution. We won't probably go that far in this class. But for this, I hope you can see that this input has a cosine pi n over 8 and an exponential or a decaying of 0.7 to the n, and that's exactly the same structure that we're having for the particular. We just have introduced a sine component in addition to the cosine. And that gives us then this delay in the output versus the overall. Or you could have said, well, now did that answer your question? That's the particular structure. What's the complete solution? The complete solution now is the particular plus the homogeneous. So that now the total solution structure is now, let's say, alpha 1 bar 0.5 to the n plus alpha 2 bar 0.9 to the n plus a beta 1 bar 0.7 to the n. And now, just to be a little different, I'll say plus a gamma. And that plus gamma is really just another way of saying, oh, you also could have a beta 2 bar 0.7 n sine of pi over 8n. Because you could use the trig relationship to convert that cosine of a plus b to cosine a cosine b minus sine a sine b. You could also, if I wanted to, I could say, suppose I now give you, given a pole zero diagram, for some waveform. So here's now the transform of a waveform. What is the structure of the time domain waveform little x of n? So that now maybe I give you 0.75 plus J 0.25, 0.75 minus J 0.25, and maybe this is at 0.5, and I throw some zeros in there, where this is now the z-plane. You should be able to now find the structure of your x of n based on that pole zero pattern. It'll depend only on the poles. You'll have a 0.5 raised to the n, and then you might want to convert that 0.75 plus j 0.25 to polar form, get its r and its angle, and then you have that angle in the argument of your cosine and sine. Losing my voice. Are there other questions? Yes.
The homogeneous structure will also have cosine and sine in this case with the complex.
Pardon?
So the homogeneous structure will also have cosine and sine with complex poles.
So now with the complex poles, we're going to have a sine and a cosine exponentially damped. So the damping will be determined by their radius. The question, I think, was when we have complex conjugate poles, does that give rise to sines and cosines? It would be pure sines and cosines if they were on the unit circle, but since they're inside the unit circle, they're going to be exponentially damped sines and cosines. The angle or the argument in that sine and cosine depends on the angle of those poles, and the exponential damping depends on their radius away from the origin. So you would now find the hypotenuse associated with 0.75 plus j 0.75. That would be the r. And then you would find the angle, and that would be the inverse tangent of 0.25 over 0.75, or the inverse tangent of 1/3. Pardon? From the origin. So now this is there's the angle and there's the radius, so that your response, which was an x of n, would be 0.5 to the n with some scaling, alpha 1, plus an alpha 2, r to the n cosine of, now let's just say, theta to the n plus some gamma. Or it could be cosine theta n and sine theta n, all scaled by r to the n. Yes?
Just double check to find the structure of x and use this to get the transfer function.
So now what I'm doing is I'm simply using the pole locations. I didn't even have to get the transfer function. I just said, oh, from those pole locations, I can actually find how this system will naturally want to shake. It naturally, if somebody walked up to it and kicked it, or if they energized the initial conditions of this system, it would naturally want to shake relative to those pole locations. And those pole locations now are some distance away from the origin and at some angle. So that the 1 is real. That has an exponential damping of 0.5. The r is now this square root of 0.75 squared plus 0.25 squared. And that's how you would find its response. And theta is the opposite over the adjacent. That's probably enough to keep us going for a little while for exam number 1. And good luck. Look at some of the practice exams, but this should give you some insight into the thought process behind solving these problems.